As far back as human history goes, humans have looked up to the sky in wonder. We've looked up there at the moon and the stars and thought, are those the gods? Are those the ancestors? Or simply, what are those? But perhaps the most important question anyone's asked when looking up at our night sky is what we're talking about today, and that is there anybody out there? Many people have asked these questions over the centuries. Hipparchus, Tycho Brahe, Sir Isaac Newton, Kepler, Copernicus, Halley, Leavitt, Messier, Cassini, Kuiper, and many more. But one person not too long ago decided it was time to truly discuss the question of whether or not we're alone out here. In 1961, astrophysicist Dr. Frank Drake put that question in a formula format to help estimate the probability of whether or not we're alone in our galaxy. Today, I'm going to explore the probabilities of finding intelligent life outside of our own, which has technologically developed to the point where they can at least send or transmit a detectable signal. Now, the fun thing about these numbers is that several of them are pure speculation. It's up to the individual investigator to determine through research what they feel the numbers should be. Basically, we're making up a good chunk of the numbers for the equation as we go along here. This is Drake it till you make it. Contact, or as I like to say, calculating out the number of technologically advanced cosmic thinkers. Wait, is that Italy? In space?
Oh, it's just Chuck Testa.
This is the Drake equation. Wait a minute, that's not the right graphic. That's XKCD comic of the Flake equation. Close, but not the same. Now that's better. Now, before we jump into what all those numbers mean, let's define what Dr. Drake was really trying to do here. This wasn't an exact formula. It was a probabilistic formula to help bring about a science-based discussion at the first meeting on SETI, which would later become the SETI Institute. And if you're not aware, SETI stands for the Search for Extraterrestrial Intelligence. Now, let's get back to the equation itself so we can get into the numbers. Let's start at the beginning of the formula with our star. Again, this is the rate at which stellar formation resulting in a star that can sustain life happens per year in our galaxy. Some estimates reach as far as somewhere between 1 to 10 stars per year, but that's actually a bit high. According to an article in the Astronomical Journal from 2011 by Chomiak and Pavich, true stellar formation occurs at a rate of approximately 1.9, give or take 0.4 stellar masses per year. In an article from 2022 published on Astronomy.com and written by Annette Ferguson, professor of astrophysics at the University of Edinburgh in Scotland, the rate of stellar formation in the Milky Way is actually somewhere between 1 to 2 stellar masses per year. But here's the thing, stellar masses don't always directly equate to the number of stars formed. Most of the stars in the Milky Way are actually low-mass red dwarf stars. These stars are substantially smaller than our sun, which our sun is the basis of what a solar mass is, aka one solar mass equals one average G2V star. So for the purposes of our exercise today, we will take those two source numbers and utilize the average between them for our R star value. If we average the Chomiak-Pavich number with the Astronomy.com number, we get an R star value of 2.15. For simplicity, we're going to assume all new stars to be sun-like G-type stars and that they will all reside within the habitable zone of the Milky Way. Let's move on to determining the value for FP, or the fraction of those stars suitable for life with planetary systems. It wasn't until about 1995, just 30 years ago, that humanity actually confirmed exoplanets, or planets that orbit stars other than our own. And with technological advances such as the Kepler Orbital Telescope and knowing how to look for exoplanet, that number's gotten pretty high actually. In fact, as of December 11th, 2025, the count is currently at 6,061 confirmed exoplanets. In an article on NASA's website, it is stated that astronomers believe nearly every single star could have at least one planet. To go even further, an article in Nature by Cassian et al. In 2012 states, we find that on average every star has 1.6, give or take 0.72 to 0.89 planets. So for FP, I'm going to actually go with the conservative side of that number with the other numbers, and I'm going to say our value is 1 or 100%. But now we need to determine the fraction of planetary systems that contain at least one potentially habitable planet. This will be the value for our NE portion of the equation. This means the planet needs to have liquid water and a breathable protective atmosphere, the correct building blocks for life like carbon, hydrogen, and oxygen, all in a stable environment, all while being sufficient mass and orbiting a suitable star, or the stars that we got from our star number, all within those stars' habitable zones. In the Proceedings of the National Academy of Sciences of the United States of America article called Prevalence of Earth-Sized Planets Orbiting Sun-like Stars by Pettigrew, Howard, and Marcy in 2013, it's concluded that, quote, we find that 22% of sun-like stars harbor Earth-sized planets orbiting in their habitable zones. Now, 22% or 0.22 seems like a low number. However, a 2020 article by Frank Tavares on NASA's website posits in a conservative take that at minimum 7% of sun-like stars have terrestrial rocky, potentially habitable planets, and a high value of about 50% or more. So let's once more go with the average of 7% on the low end, 22% at the midpoint, and 50% on the high end. Average out, this means that of suitable stars with planets, about 26%, rounding down, or 0.26 have planets within the habitable zone. Now, for those planets suitable for life, we need to determine what percentage of those planets actually have life appear, which is our FL value. This value doesn't concern intelligent life, just, well, life. We've found many places out there that have the building blocks for life. We've even found amino acids in our own asteroids and comets, but that's chemistry, not life. Unlike stars or planets, we at present have no way to directly measure how often life begins out there. But we do know from our course this semester that a sun-like star has enough room in its habitable zone for about 2 to 3 terrestrial planets. In our case, we have Earth, and on the edge of our HZ is Mars. Even though currently it doesn't harbor life, Mars potentially at one point met at least part of the requirements to do so. So in this case, one of 2 planets generates life. That gives us an FL number of 0.5 or 50%. But if we stick with the 3 planets per habitable zone and say life still only emerges on one, that gives us an FL number of 0.33 or 33%. There's also the opinion of Harvard and the Smithsonian's Center for Astrophysics, which state that approximately 1.3% or 0.013 of the known exoplanets contain water and other required elements for life. Combined and averaged, these sources give us an average of 28.1%. These estimates are based on very different assumptions, but averaging them helps us illustrate the uncertainty of this term for the problem. But that's just the basic cellular life. We're looking for intelligent life for our FI value. But before we can figure out FI, we must first define what intelligent life is. I think our baseline here is agreed to be humanity, but where exactly in human history did we become intelligent? Many believe intelligent life must be sapient, that is, capable of reasoning, self-reflection, and long-term planning. Some definitions go even further, arguing that intelligence requires moral reasoning or empathy. Rather than tying intelligence to morality, for this project, I'll define intelligent life more conservatively as being a civilization who looks up at their night sky and asks the question, what's out there? Dr. Drake's original estimate for FI was 0.01 or 1%. The belief was that wherever life formed, intelligent life was bound to follow. And to add to this number, we'll pull some estimates from Peter Ward and Donald Brownlee's published book, Rare Earth Why Complex Life is Uncommon in the Universe. And averaged out, that's going to give us an average FI number of 0.0115 or 1.15%. Now we need to determine our value for FC, that is, the fraction of those planets which develop intelligent life whose civilization transmits signals detectable at an interstellar range. In January 2018, when I was a truck driver, I came across the Very Large Array, or VLA, in New Mexico. The VLA doesn't just announce itself, it appears. Row after row of silent antennas listening to the sky over the New Mexico desert. But I'm not talking about this just to show you my personal slideshow. The VLA in New Mexico, the SETI array at Hat Creek near Redding, California, they're all listening for signals being transmitted by extraterrestrial life. Problem is, we still haven't heard anything solid, but there are certain constraints on why that may be. Radio signals, which is the base for interstellar communication in our equation here, is limited to the speed of light. The speed of light, as you know, is the fastest speed anything in the universe can travel. Well, unless you count Spaceball 1.
No, light speed is too slow. Light speed too slow? Yes, we're gonna have to go right to ludicrous speed. Ludicrous speed. What the hell was that? Spaceball 1. They've gone to plaid.
But seriously, short of some sci-fi-ish subspace communication device being invented, signals are constrained to the speed of light. For instance, humans have been intentionally broadcasting radio signals for about 80 years. At the speed of light, that means our own signals have only crested about 80 light years of distance. We're trying to determine what fraction of worlds with intelligent life develop technology capable of interstellar communications. The truth is, we have no way of knowing the number for communicating civilizations. We could be the only ones. We can be the first ones. Heck, we could be the last one. Frank Drake's original estimates for FC were 0.10 or 10% to 0.20 or 20%. So we will again use the average of 0.15 or 15% for this number. But personally, I've watched too much sci-fi to believe that's all the fraction of the type 1 or higher civilizations out there. I'm going to say that fraction is 0.75 or 75%. So, like I like to do, let's meet in the middle on this one and take the average of the two numbers, and we're going to say 0.45 or 45% for our FC value. And now we're on to the last variable of the Drake equation, L. This is where we need to determine the length of time that civilizations that have made it through the rest of the equation's filters are able to release detectable signals into space. space. And this is where it can get a bit scary. If life is supposed to exist out there, why haven't we spotted signs of it? Maybe perhaps, if there were transmitted civilizations out there, they just didn't make it that long. Maybe we're just not listening on the right frequency or technology. There's a lot of maybes in there, and that's kind of what the whole point of the Drake equation is. It's more of a thought exercise than an actual mathematical equation, and that's okay. We get to have more fun with it that way. So let's take a few numbers to gather an average amount of time for L. In doing this, I'm going to pull numbers as they relate to the age of humanity from some of my favorite works of science fiction, and we'll assume for the purposes of this project that humanity has been sending signals out into space since the beginning of its modern existence, around 0 CE. In Isaac Asimov's Foundation series, humanity is about 26,000 years old. In Frank Herbert's Dune, 22,000 years. In Kim McLeod's Engines of Light trilogy, about 10,000 years. Gene Roddenberry's Star Trek, specifically going up to where Discovery ended out, 3,100 years. Don Bluth's Titan AE, 3,000 years. Eric Nyland and a bunch of other authors with Halo, we're looking at about 2,500 years. Josh Whedon's Firefly/Serenity, that was 2,500 years. Seth MacFarlane, The Orville, 2,400 years. James S.A. Corey, aka Daniel Abraham and Ty Frank, with what I think to be the best, closest hard sci-fi book I've ever read, or book series, I should say, The Expanse, at 2,350 years. Those lengths of times, although found in sci-fi, are as good of estimations as any we have at this point in time. If we average those 9 numbers out, we get an L value of approximately 8,205.5 years of transmitting lifetime. In the end, the estimations I've made conclude there should be about 6.67. Sorry, I had to do that. The kids love it for some reason. But seriously, the estimations do conclude there should be about 6.67 advanced communicative civilizations within the Milky Way. If we round that up to 7 and obviously include ourselves in that number, then there should be about 6 other civilizations we're not in contact with, nor can we detect. The fun thing about the Drake equation is that it's like, whose line is it anyway? You get to make up the numbers as you go along.
That's right, the points don't matter, just like the word international in International House of Pancakes.
Drake's original estimate was somewhere in the neighborhood of 10,000 communicating civilizations. Some people's numbers point to pretty much 0, which is, to me, surprising since, we know we're here. I think we all share a common curiosity about the cosmos. That's why you're here watching this, right? Well, except for my professor. He's here watching it to grade him a project. Hi, Professor Trinto. I just want to say thanks for watching. Hopefully you enjoyed the thoughts of an astronomy student on this subject. And as one final thought to ponder, Carl Sagan is attributed as saying somewhere something incredible is waiting to be known. And whether that's 6 more civilizations or 6 million, or even if it turns out it's just us out here in the void, the search itself may be the most human thing we'll ever do. So until aliens either invade, slide into our DMs, or finally return our radio calls, I guess we'll just keep doing math and staring into the night sky, looking for answers.